last lecture. So we considered this notion of singular homology groups with coefficients in some abelian group G, and very briefly, so they were defined as so for some topological space M, they were defined as well as a set. They were defined which has a natural group such as a set of linear functions on the chains with integer coefficients on M to one group G, such they are closed, meaning that if they are evaluated on a boundary of any chain, they are automatically must be zero, and there is equivalence relation where we can add to this A's something which is called cochain, so we can add kind of composition, can add to a composition of some A prime with a boundary operation, because this is we called co-boundary of A prime. And then we consider a notion of Poincare duality. So for the M is closed. We have a special case when M is close to oriented manifold. It's formulated just isomorphism of between this is a d-dimensional manifold as isomorphism between M's cohomology groups and d minus M's homology group, but well, there exist versions for manifolds, non-closed manifolds, meaning that there is some non-empty boundary and unoriented. They kind of have a similar formulation, but slightly different. But at least I'm assuming that M is oriented and has no boundary. So geometrically, this Poincare duality worked in this way that if you have a class in homology represented by some chain, and it corresponds to some class in cohomology, the relation is as following. So we can see the C again. We can understand our chains which have no boundary, meaning the cycles, as a kind of network of simplices in kind of inside in M. Alpha 1, alpha 2, alpha 3, and so on, which are colored by elements of the group, and 1, and 2, and 3. So Ni. Okay, here my group. So I can see that my group is sorry, G. And then so to understand this, what the relation with the cochain A representing class B is the following. So if I evaluate A on some, I can consider, so this is A, therefore, kind of functions on the chain. So if I consider its kind of value on some, let me do it in some value on some gamma, it's which is here, it's M chain, and this is this was D minus M chain, which is actually a cycle because it's represent a class in homology. Then yeah, so this A this value can be understood as a sum. We can essentially sum over all these kind of intersection points where this gamma intersects our chain C, and they have their kind of the dimension add up to the dimension manifold. That's why generically they intersect. If you kind of assume that generically they intersect over just a bunch of points, and we kind of do this sum of intersection of these images of alphas with images of gamma. Okay, and then we also discussed what is kind of this notion, some very briefly discussed with the notion of characteristic classes. In particular example, so this was so we and kind of their correspondence, how they describe gauge field configuration, in particular for U1 gauge fields configuration. We can associate first chain class, which is an element in the second cohomology of our space-time with integer coefficients. And in this particular case, this gives a complete classification of gauge bundle up to isomorphism. And then we also consider the case of SU2 gauge field, and then we consider the notion of second chain class, which is valued in the fourth cohomology of a space-time. And then we also consider SOM gauge field. And here we had second Stiefel-Whitney class in the second cohomology of space-time with the two coefficients. And then we started discussing kind of topological discrete G gauge theory. And the first step was kind of defining what should be a fields in our theory, and the next step would be defining what is the action in the theory. So and for the field, so G is assumed to be some discrete group, which by default we also assume to be abelian. So kind of and we there was a kind of some motivation. We arrived at the conclusion that the gauge field naturally corresponds to one cochains with coefficients in our gauge group G, and they are should be closed, meaning by definition, so A composition with boundary is 0, and so the meaning of value of this cochain on a one chain, so which is basically generated by some sort of intervals inside our space-time, is that it's a parallel kind of, okay, it's yeah, here assuming it's one simplex, which is well, it's a map from delta 1, which is an interval to our space-time M, and so this has meaning of kind of holonomy or parallel transport along path gamma, and particularly if you have some sort of field and for charged field phi in a representation rho of G. When we do this parallel transport, this phi is multiplied by the representation of this A of gamma. A of gamma is an element of G by definition. And then we said that Poincare dual which is a class in D-1 dimensional homology with coefficient in G to kind of B, which is a class of A, and this so this homology class, as we argued, this contains gauge invariant information, has meaning. So this C has meaning of network of charge operators in a quantum field theory, and I said that I'm going to elaborate on this in the next lecture, and this is what I'm going to do now. So, so the statement, more precise, the statement is the following. So if G is a global symmetry in a QFT, and so B is a background gauge field for this gauge field for this discrete, so G is some discrete group. So this C is a network, has a meaning of network of charge operators in quantum field theory. So why is that? So let's kind of go back to the kind of the most usual case, which many of you are familiar with. So kind of consider more usual charge operators first. For example, for continuous symmetry G, let's say for simplicity take it U1, and one of the most common case, and consider the case when our space-time is kind of this special form. It's a product of some D-1 dimensional kind of space and R, which is the time. And so you can kind of understand this is some sort of cylinder. And then what is it kind of, we can have a G is a current. Classically, we can consider for U1 global symmetry, we can consider associated neutral current. And then the charge, neutral charge, is at some sort of, well, in principle, it's defined for some time, kind of value t. It's an integral of in terms of differential forms. So J is a current is like one form, and so the charge is a integral over star of J over kind of particular spatial slice at time t. And so we know that it's kind of since we have a symmetry, so this J is conserved, meaning that D star of J is 0. So this is just divergence in terms of this differential in terms of exterior derivative and the Hodge star operator. And this implied by Stokes theorem that Q of t is independent of t. And of course, this is only statement kind of local. Locally, by locally means away from charge operators. have some sort of we can kind of place by, of course, we can by hand place some sort of charge, kind of for this symmetry, and then of course the divergence of the current kind of source for this symmetry, source for this current, and then kind of it will be not conserved at this particular point, but it will be conserved everywhere it's outside. And then, okay, this is what happens kind of classically, and quantum mechanically. Okay, we replace these kind of fields, and we replace everything with operators. And so for quantum field, phi hat in a representation rho now of U1, we have so okay, what is the representation of U1? So representation of U1 are all reducible representations are one-dimensional. So we can just assume this phi is just kind of classically is just some complex Wallet field, and so the representations are labeled basically by integer numbers, which are charged. The reducible representations are labeled by kind of integer numbers, which physically has meaning of the kind of charge, the amount of charge, more precisely. So if G is, we consider some element of U1 of the form exponent of I alpha. So we can consider representation, which is rho is I and alpha. So kind of if we act, meaning if we this phi field should be multiplied, if you act by some sort of this element G on phi, this phi is multiplied by I and alpha. And in particular, this means that the commutator of quantum mechanical commutator of my charge, now operator with phi, is n phi. So this can be also understood in this way. And what we can also consider kind of this Q corresponds to kind of infinitesimal U1 transformation, but we can also consider operator which corresponds to a finite G transformation, which is will be exponent of I Q hat, and it will satisfy this kind of together with phi operator. It will satisfy this usual unitary transformation property, kind of the statement that in quantum system, in quantum kind of mechanics and quantum field theory in general, all kind of yeah, the symmetry transformation should correspond to unitary operators, and this U is this unitary operator, and the kind of adjoint action of this U does multiply this field by rho of G, but this can be rewritten in this in the way that U hat G phi is equal to rho of G. So here rho is just a phase in this particular example. So on the level of operators we have this, but what about in terms of kind of correlation functions or insertions in the path integral? In terms of correlation functions, this can be this is equivalent to the following statement, that if we kind of consider my field at some sort of time t, okay, we also fix some kind of special position. So this is phi of kind of x and t somewhere in our space-time, and then we consider this operator UG at let's say t plus epsilon. So we put it here. So it's a operator extended along the whole spatial slide, because it's given by integral of a current over this d minus one dimensional spatial slide. Okay. So, and the statement about commutation means that if we instead consider this operator at time t minus epsilon, this will kind of result. This will cost us the kind of multiplication by this extra factor. This is because we know that the if we kind of when we insert our fields in the correlators, quantum mechanically this corresponds to insert kind of considering operators which are ordered according to the time ordering. So if I place so this kind of if I place this u in the first kind of instance at a time later than 5t, this will correspond to this ordering. And if I place in the second instance, I place it at the time before phi, it will correspond to this ordering. So this can be understood that this kind of relation in terms of insertion of kind of operators in the path integral can be understood as the following properties, that if we can consider this relation as the following. So we have phi, but in the second instance, we put this u operator below, so kind of early in time, and this kind of exchange costs us this extra phase rho g. And this can be seen as well. So locally, as we saw, we kind of this u is independent of t, which correspond to conservation of the current. But if you kind of if you move it kind of across this phi, and when phi crosses this charge operator, we get this extra phase. And this is exactly what we observe, what we had in this kind of parallel transport picture when we did a parallel transport along the kind of some paths. Whenever this path kind of path crossed cross this kind of one of these simplices in my kind of chain realizing the Poincare dual of my gauge field, we earned a kind of extra kind of, we added to this kind of group element the elements which will color a particular kind of a particular defect in this network. So namely, if you go back to this kind of for discrete G, then we see that so this class of C Poincare dual to gauge field. So here we have a considered kind of, so far we consider global symmetry, so this hasn't really show background gauge field. The C is Ni alpha I. Again, you can kind of visualize as some sort of network of these alphas. And colored by these elements of the group. So then we can understand this image of I of a particular defect in this network as a support of a charge operator U and I, where Ni is and deformations of the network charge operators can be understood as gauge transformation. So it changes. So it changes A, this cochain, but not B, which is a class of in H1. Okay, maybe now I should pause for questions. Is there something in the chart?
Yeah, I think there's some questions in the chat.
Yeah, this okay. This chart is yes, yeah. Classically, yeah, you just charge in this usual charge in the sense of node. When we talk about the continuous symmetries. But of course, when we have a discrete symmetry, there is no notion of current, so we cannot define charge as some sort of integral over current, but we can still define it in this way, as we did it. As if you cross the field, kind of if we kind of move this charge operator in the correlation function and it crosses position of a charged local operator, it gives us extra kind of its effect is multiplying, changing this local operator according to its representation. Perhaps ut minus epsilon should be placed to the right. Well, here it doesn't. When I write correlators, it doesn't really matter because it's just insertions of kind of. I understand some sort of insertions in past integral. I mean, of course, if I now will interpret this as some sort of kind of some expectation value of these of the corresponding operators inserted, then of course they will be ordered so like that, yes. But in the correlation function here it's it doesn't really. I mean, they will be automatically ordered. Any other questions? Yeah, I guess not. Okay, and this everything here can be generalized to what is called high-form symmetries. Let me write it: P-1 symmetries. And so here, and what we mean by this in our context is that now the background gauge field again, the gauge invariant data of the background gauge field is a piece cohomology class, and it's represented by some P cochain A, and with the Poincare duality tells us this should be isomorphic to D minus P's homology, and here we'll have some Poincare dual chain. All these exchanged by Poincare duality, and now we have kind of similar interpretation in the following sense. So we have a kind of charge. So this C can be thought as a network of D minus P dimensional charge operators, and we have now the charged objects are no longer kind of local operators, but they are now P minus 1 dimension. And so one way to understand this is that we can consider kind of if you have P minus 1 dimensional kind of charged object, we can consider the parallel transport along sigma, which now is not a path as was before, but some p-dimensional submanifold. So instead of so you can imagine it's hard to draw, but you can imagine something in the form. So we have some sort of p minus one-dimensional extended. So now it's extended charged operator in our theory, and then we do parallel transport along some sigma to some another position, and then we have this network of C and I alpha I charge operators, which are now D minus P dimensional charge operators. And there's kind of similar relation that the kind of this holonomy is given by, so kind of when we do parallel transport, so let me consider if this charge operator is something like, let me denote it, or. So this or is multiplied by rho of g when we do this parallel transport. And this g is again can be understood as obtained by counting all intersections, taking sum over all intersections of this image of alpha I, which is our charge operator, kind of places where we have supported the charge operators with sigma. This is kind of analog, but completely analogous to what we had before, but we changed the dimension as different. And another remark, okay, we consider it, going back to the p equals 0 case, where we have the usual kind of zero form symmetries. Of course, this, so we consider this g by default to be abelian, but this case is well defined also for non-abelian g, and kind of in place the usual first homology. We consider one should consider homomorphism from the fundamental group to G modular conjugacy action, and this is a kind of gauge invariant. So this kind of, we can consider loops which represent classes in the fundamental group, and then if we have some sort of B class B in these quotient over conjugacy classes, so we okay, yeah, well, let's consider B. Well, let's consider just A, which is without this quotient over conjugation. So we have kind of for loop A, gamma, but we assign A of gamma, which is element of G. But it's not necessarily gauge invariant, because if you have some sort of gauge transformation for gauge transformation, so if this loop base it at some sort of you start loop from kind of from x0 into x0, which means that in the fundamental group we consider the base point being this x0. So if for gauge transformation, which is a continuous map from our space-time to a group. This A of gamma changes by G of x0 times A of gamma G inverse of x0. So it can change like this, but the conjugacy class is invariant. So the if the kind of the gauge invariant data is contained in this set of conjugacy classes. Any questions? Is there some question in the chat? In this way, we may have p charges that are really wedge product of charges and not quite sure what this means, but we have our well for yeah, the gauge field so far is not dynamical. Well, we can consider, of course, there. What we can have, we have like P1, two different gauge field. We can consider it's this cup product, and this will give us a gauge field for the kind of symmetry of the degree, which is the sum of the degrees, basically. So yeah, this is true in a sense. No, for zero form symmetry, U was a charge operator, and Z and phi was a charged operator. So another way around. So yeah, U. So yeah, so for zero form symmetry, U is a charge operator, and phi is charged. So this is this was d minus one dimensional, and this was 0 dimension. And for p form, we kind of now there will be a charge operators are d minus. Okay, I used this p minus. Sorry, I used the convention of p minus form symmetry. The charge will be d minus p dimensional, and the charged operators was p dimensional. So in particular, another way to distinguish them is that they have they are so these guys are labeled by elements of the group, and these or n, we also use this notation n for elements of the group, and the charge operators labeled by representations. And why it's natural? Because for U1 symmetry, representations are integer numbers, and this integer number describing expansion is exactly the charge, the amount of charge. This charge is an integer. And the same thing for p minus form symmetry. So this is labeled by group elements, and this is labeled by representations of G. The charges are differential forms now. Well, the charges, I would say, depends on the definition, but I would say charge is just charge itself is a representation, the choice of representation. That's what one calls charge. And the charged operator is some extended operator, like p form p minus one form symmetry. The charged operator is some extended operator which is colored by representation of the symmetry. but yeah, for like for discrete, yes, exactly one of the points. So for discrete symmetry, we don't really have description in terms of any like differential forms and so on. We have description in terms of co-chains or cohomology or the corresponding cohomology classes, or like instead of submanifolds, we actually more generally not any homology class can be represented by submanifold. So in general, we need to consider, but sometimes in simple cases, yes, you can represent these represent the kind of this closed the homology class by some submanifold, but in general, no, you have to read kind of network of something which locally like looks like submanifolds. But to be precise, it's a chain, which is a cycle. Instead of integration, we have this formal pairing between cohomology classes and homology classes, if you wish. Any other question? Okay. This way we consider it again. We describe what is the kind of fields of our discrete gauge theory, and the next step will be well, to describe actual dynamics. We also need to describe some sort of action. So okay, on a manifold SM, it will be some function of our field B. So this is B is in general, if it's a P kind of for P form, P minus 1 form symmetry, it's HPM G element. And so maybe let me make some remark where this discrete gauge series appears. Physics. So they actually appear in some sort of condensed matter systems, and they are supposed to describe what is known as spin liquids. And in particular, in this, so very roughly, yeah, there are some sort of you can consider some sort of spin systems like lattice systems. Well, if you consider like microscopically, they can be described by some sort of lattice system. They have some spins, which can be like spins, roughly spins up and down at each side, and these kind of these the kind of these chains, which we consider can be understood as some sort of submanifolds, where all spins are kind of down, where in the rest of the space all spins up, something like this. Yeah, I'm not really describing a lattice system in any precise way, but this is not a goal. This kind of understood as my support of my C, where this C is comparable to gauge field B, and they also appear in this kind of maybe more related to high energy theory. They are kind of what is called these SIM, kind of recently very popular notion of SIM TFTs. They can appear as SIM TFTs of some kind of non-trivial quantum field series related, in particular related to kind of real, even possibly related to a real world. This is just a remark. And if you heard some sort of word words like toric code, so toric code is a particular example of Z2 gauge theory.
Well, I just want to mention that there will be a toric code a lecture next week, by the way. So very nice.
Okay, so so next step, as I mentioned, we want to describe action, and it should be a kind of we want it to be analog of and has some similar properties to the usual action for some sort of fields which are like scalar fields or finite fields, like analog of. And the usually action is given by integral over Lagrange over kind of space-time M of a Lagrangian, which is a well, it's a D form. Well, for example, it's can be something like volume form times d mu phi for scalar fields, plus maybe like m squared for field scalar field. And so D form on M, which depends locally on phi. Okay, so first, yeah, what would be analog of integration? So analog of integration, so we basically, this is something we already discussed, but let me remind you. So there is, when I consider a cohomology group, there is a surjective map to Holmes from the homology group with integer coefficients to G. And so this map works, I think we already discussed it at some point briefly, but let me remind you. So B is some sort of, is a class of some cochain A. It is sent to a home. Well, home is supposed to be a kind of element of home is a functions on HM, which gives an element in G. And this function works as follows. So if you take C, something in HN, this function is we just say that this function is the value of my cochain A on C. To remind you, so A itself is a so this homology class represented by a certain homomorphism from Cn to G, and this has meaning as kind of can be formally written as the integral of B over C. Just by definition, it's this pairing. So basically, what I want to say, the bottom line is that there is there's well-defined pairing between nth cohomology classes and nth homology classes, and it has it's analogous to integration of differential form over some submanifolds, in a sense. And so for oriented d-dimensional M, there is a special kind of fundamental, what is known fundamental class in the this homology of Z, the homology of M with integer coefficients. It's usually denoted by class of MD, and this has a meaning like, and we consider kind of a D chain which kind of covers completely. It consists of like these simplices which cover fully our D simplices which cover fully our manifold, and so we want, in our case, action to be something like integral of Lm of B over M. But what precisely this means is this is a kind of a pairing between a fundamental class and So if you want our action to be kind of as defined as a real number, this should be LM should be element of this cohomology of M with real coefficients. And yeah, to be, I mean, this is by this, what we mean is the following. And but actually, we only need, since we're interested in quantum theory, we only need exponent of the action to be well defined. So here, of course, we assume that h bar is 1. And this means that actually we need this S to be valid only in R modulo 2 pi Z subgroup. And this is only needs to be valid R modulo 2 pi Z. Of course, this is isomorphic. This group of this coefficient group is isomorphic to U1. So this kind of our Lagrangian can be understood as a map from HP M with coefficients in G. This is where our field lives. This is gauge field. To HD, where D is the dimension of the spacetime M with coefficients R modulo 2 pi Z. In LM. And then SM is again integral of this LM. Okay, but we also want some sort of locality, nice locality property. And the locality can be formulated a formula as follows. So we want L to depend locally on B. And what does it mean? So if you can kind of consider, in a sense, it should kind of, we can consider kind of a map from some sort of M prime of M. For example, this can be, for example, inclusion map. M prime can be just kind of subspace part of the M, but in principle it can be general continuous map. And then we want that L. So now we can consider kind of a theory on M prime, and we want LM of so we can kind of, yeah, we have this notion of a pullback, so we can pull back the field. So kind of fields are pulled back with respect, we have some kind of continuous map. The fields are pulled back, and this is a pullback F prime, which we discussed. So we want this property that the kind of we can pull back this B field B over M to the field F star B or M prime, but we also can kind of pull back this Lagrangian, and this should be equivalent, the same thing. So we can kind of pull back field, but we also can consider kind of a theory on this M prime, and this should be the same. So this should be L same as Lm of pullback of Lm of B. So in particular, if F is some sort of inclusion, we can consider this M and some smaller part M prime, then this F star is just a restriction on the submanifold. And this is basically it means locality. We kind of but now kind of if we can forget about motivation, in principle we can also forget about motivation, just postulate this property, and then one kind of can argue that it's indeed defines correctly what is now local kind of topological quantum fields here, which satisfies a certain set of axioms, which we'll later consider. But at the moment, it's just we kind of we argue this property by some sort of motivation with acquiring some analogy with case of continuous field. Okay. And there's a couple of questions. So it's not, but it's analogous, right? Kind of generation of yes, it's analogous, and it's reduces to the usual integration. I mean, using this de Rham isomorphism, it's when you consider kind of de Rham homology with coefficient in R, this this becomes equivalent to the usual integration. But otherwise, it's just kind of analogous. And because we are not these kind of cohomology classes in for general G, they're not relied by any differential forms. But if the coefficients are, they are relied by differential forms, and in this case, the notions of this integration coincide. Okay, so another question: why do we need to do 2 pi iz quotient over R? So our goal is to define some sort of path integral. So in the usual case, the path integral looks something like this, right? So and you might consider insertion. We integrate over all fields from M to well some target space, and so usually the usual fields are some sort of functions on M, material functions, or well sometimes they can also be differential form. It doesn't matter. So we want to kind of define an arc of this. Okay, and we also assume that h bar is equal to 1, but this can be always achieved by just rescaling action. So we so to define this, we need to define this second path integral. We need to define actually not S, but I explain to IS. And it could be that so we know that if S if you change S by 2 pi n, where n is an integer, this exponent of IS doesn't change, so it goes to itself. So we can formally understand as S not real valid, but valid in R in this quotient. Because this exp one can assume as a well-defined function from R mod to like exp I of something. So this is I something is a function for R mod 2 pi z to U1 to face for our well, this is basically isomorphism. Any other questions? Okay, so another way to understand this is that we have the following commutative diagram, this kind of property, locality property. This commutative diagram. So we can, so we have M, yeah, we have a map from M prime to M, F, two different spacetimes. Again, one can be just kind of subspace time in the other. It's kind of just some sort of patch. And then we have this LM. So this is our fields. The first row is where our fields live, and this is where our Lagrangian. This is HD. So this should be so this is LM, and this is L prime. So this should be commutative, and this should work for any M and M prime, and a map F between them. And this this has this type of kind of structure is what is known in algebraic topology as a cohomology operation. So this L kind of, if you consider a collection of all Lagrangian for any m's, this is what is known as a cohomology operation by definition. Basically, by definition of this of what is called cohomology. And it's usually written as kind of in this way. So we kind of kind of can have a dot means we can put it any m there, and it transforms like this. And more formally, and I will elaborate what this means next. This is what is called a natural transformation. Between, also this is by definition what is called natural transformation, essentially natural transformation between two contravariant functors from the category of topological spaces to a category of abelian groups. But yeah, so I will to kind of to explain this, I need, and I also will need some sort of a category theory later. So next step will be give us some sort of very brief reminder of basic concepts in category theory. And I will explain what is, in particular, I will explain what is a natural transformation in general. But okay, are there any questions up to this? I don't know if you need to do a quick break or we just continue. You will let me know.
I think it's up to you. Maybe we take 5 minutes break. That's fine.
Okay, let's take 5-minute break. Yeah, sure. Okay, next step will be some very brief review of category theory. Yeah, I know that many of you may know about it, but some of you may not. So and we will need it later. So I will give a very brief review. So first, okay, what is the notion of a category? because yeah, I was asked to be some sort of pedagogical. So it's a kind of collection of the following, but I will be not very formal. So a category is consists of the following data. First, a collection of objects, often called ob-C, and for a pair of objects O1 or 2, we have a collection of what is called morphisms, which is denoted as hom O1, O2, and we can also understand as a kind of this morphism as arrows, kind of O1, 2, like maps, which kind of if the kind of standard example one has in mind is a kind of category of sets where objects are sets, and the morphism are just functional between sets. And with the composition rule we have an arrow from O1 to O2, and then the arrow from O2 to O3. There is a rule, FG is a rule which associates to this pair, there must exist a special arrow from O1 to O3, which is denoted by this G composed with F. And formally, this is this map from a product of collection of homes to a third collection of home, and it satisfies some associativity condition as you would for like composition of functions. Okay, and so this, again, the standard examples are the category of sets. So objects are sets, and the morphisms are functions. Then one important category which is relevant for us is often the top. So objects are topological spaces, and homes, the morphism between objects are well, continuous maps. Then we consider top star, which is a pointed topological spaces. And this is something we we saw in the first lecture. So the objects now are pairs, topological space and a point inside it, and the morphisms we define. So the distinguished points should go to distinguished point in the other space. And we can also consider category of groups, objects and groups, and the morphisms are homomorphisms, the usual homomorphisms. And there is also, one can also consider category of abelian groups. Okay, and then one can consider notion of functor. Between two categories. So A, B are some categories. And so it's contains the following data. So for each X object in A, we need to define associate f of x, which is the object in B. And we also need to define kind of a map on the morphisms. So if we have a morphisms f from x to y, it's the element of a form x, y. To it, we must associate an arrow from f of x to f of y. And this is usually not f of this. Okay. So what are the basic examples of functors? Is what is one can consider forgettable functor. For example, from top star to top. So we we forget about this marked point. So for a kind of for a space with a point, we just forget about this point and we just associate this topological space. And we consider forgetful functor from top to set, so which means we forget about topology, or we can consider forgetful functor from the category of groups to set, where we forget about the group structure. Then kind of in a bit different direction, we can consider inclusion of abelian groups into all groups, kind of subcategory. And okay, what is the less trivial things is something we saw already in this course. It's homotopy groups. So it can be understood as functors on from top star, the category of pointed topological spaces, to a category of groups. Then homology groups. Coefficient G is can be the functor from top to group. Well, actually to abelian groups. And we can consider cohomology groups. And here the kind of if you have this f, which is reminds of f, which was a map between topological. How does this functor work? Why is this a functor? Because if f is a map from x to y, we take it to this f star, the push forward on the cohomology groups. Then I can say cohomology groups, and this is a kind of the functor from top to groups. But if you want to understand this kind of functor in the usual way, this is a we should consider opposite category, which means direction of arrows is reversed. Of arrows is reversed. Or instead, one can call it what is called contravariant functor. And this is, so in particular, this f, the map goes between the goes to a pullback map, but we know that this is pullback is acts in the opposite direction. That's why we need to consider this opposite functor. So let me write it maybe explicitly. So this, if you have how this functor works, so f was mapped from like topological, so this is some element in objects of top. And this we take it, this functor f is taken to well, this homology functor. It's taken to, well, x is taken to h, and x, g, and y is taken to h and x, y, g, and the map is taken to pull back, but the direction of the arrow is reversed. Yeah, and here, of course, yeah, I can consider yeah, not just yeah, I can just consider abelian groups. I mean, of course, I can also consider all loops. Okay. Any questions so far?
Sorry, what does the middle arrow mean? The HN.
Well, it's how, so the middle arrow means it's a map on the homes. Yeah, it's well, if we pretend the homes is a set, so it's just the middle arrow is it's how, so F is the element of home X, Y, and in particular the functor gives me a map from so this functor F must provide a map to this, but this is Hn of X, and this is, well, F here is Hn basically.
Okay, thank you
So
very
the
much.
middle map is a map on the kind of on the homes, on the morphisms, and the up and bottom map. These are maps on the objects.
Okay, thank you.
Is a canonical quantization a functor? Maybe I should. Yeah. Well, I guess probably in some proper categories it is, but let me. Yeah, I think in some sense it's a functor. So maybe one should be careful. And then, yeah, so then functor which associates some Hilbert space. But we, well, depends. Okay, if you consider this kind of space is the is it like category where it tags on is the domain category is like category of spaces. But because we can also consider kind of quantization kind of some particles here on a given space time. And this is a kind of the Hilbert spaces form a functor on the category of this well, spatial manifolds, and then this is also a functor. Okay, and okay, so what about natural transformation between functors? Let me look. Natural transformation lambda between functors. F, so we have now two different functors from category A to category B. So, so natural transformation is a collection for maps kind of lambda x. So for each x, which is an object, x object in A, you want to define an arrow from f of x to g of x. Such that for any homomorphism from x to y, so any arrow from x to y, we have the following commutative diagram. So the okay, if you apply functor f, then we get the following, right? We have a map from f of x to f of y. Now, if we apply the functor f prime, sorry, g, sorry, by g I mean f prime, because g is not defined. Now can I apply instead functor f prime? This will give me the following. And but here I have a map lambda x, and here I have lambda y, and this must be commutative. So whenever I have this kind of collection of maps which satisfy this commutativity for any arrow f, this is what is called natural functor. So natural transformation between two functors. And this is exactly, so what we saw is indeed was a natural transformation between cohomology functors. Maybe let me give you kind of just to say that there are other examples of natural transformation. For example, you can consider two functors from a category of group to itself. The first is an identity functor, and the second functor will be abelianization functor. So we consider group and we consider even abelianizer. So we divide by the commutator subgroup. So G goes to G divided by the commutators. And there's a natural kind of yeah. So what is the natural transformation? So if you have a kind of map from homomorphism from G F to G, we can consider kind of these by G, map by G, which is a projection map from G. And okay, here I understand this is the arrow between objects, right? But here I consider a homomorphism. So pi G is a homomorphism, which is a projection. A quotient map, right? G. And then I can do the same for H. And then I consider kind of abelianized kind of restriction. This F, the homomorphism F descends to a homomorphism on the abelianization. And they have this commutative diagram. So this kind of the abelianization, this map, which is a quotient map on the commutative subgroup, is a natural transformation between an identity functor and abelianization functor. But okay, this is what we are interested in in the context of this construction of actions for discrete gauge series is this cohomological operations. So more generally, a cohomological maybe it's just called a cohomology operation lambda of type, what is called of type, this is the definition of type P, Q, G, and G prime is a natural transformation between two cohomology functors. So in our case, to understand these cohomology operations in particular case when this Q is dimension of our theory and G prime is basically U1. But okay, before we proceed with kind of explicit description of such natural transformations, let me mention kind of the following a sort of different realization of gauge fields, which you can often see in the literature. But maybe, yeah, so this was the end of the brief kind of review of necessary category theory stuff. Is there any questions for this part? If not, okay, let me proceed. So a different realization of a discrete gauge field. So before, so at the moment we consider kind of gauge fields, well, up to gauge transformations as elements of cohomology. And there is a statement that this, well, let me say so far as a set, but we can consider also the isomorphism as groups. So it's a set of homotopy classes from M to a certain topological space, which is called Eilenberg-MacLeod space. So this bracket notation we already saw it in the first lecture. So it's by definition it's we consider maps, continuous maps up to homotopy. And okay, so what is this topological space KGP? So it's defined for any G and P some natural number. Well, possibly it can be 0. So up to homotopy equivalence. Okay, there's some fine print for this statement, which I explain later what this means, but in principle you can ignore this fine print. Up to homotopy equivalence is defined by the property such that its homotopy groups so yeah, is uniquely defined up to homotopy equivalence by the following process. These homotopy groups are equal to G when n equals P, and it's trivial when otherwise. This special topological space where all homotopy groups are concentrated in a certain degree. And in this degree where they're not trivial, they are given by this prescribed group G, which we have. And of course, G here, G, we assume G to be abelian. Because when in the special case when P equals 1, the G may be non-abelian. And one can show once they are they have this special property, it's this is what is known as Brown representability theorem. It's known that the elements of the cohomology group, they are in a natural bijection with this set of homotopy classes from our M topological space to this. So what is this fine print, which again you can ignore? So this is assuming isof to if this space, we are looking for the space, these kind of spaces which have this special property. There's what is called CW complexes. Or instead we are considering, instead of homotopy equivalence, we consider what is called weak homotopy equivalence. which is kind of slightly relaxed, a certain relaxation of the usual homotopy. But again, this is just to be kind of precise. But again, you can ignore this fine print. And there are some sort of explicit construct. In any case, there is a given G and P. There is explicit kind of construction of this topological space. There are some questions. Sometimes we meet notation K pi. What is the meaning of pi? Well, I don't know. Pi is any, if it's in the context of Algebraic spaces, can be any group. Okay, and when we have one, the first Algebraic place, this actually can be also non-abelian. Yeah, in our context, yeah, in principle, this can be in group. So depending on the context. So here, this instead of pi, I have G now. So if we use this relation between cohomology groups and homotopy classes of maps, we can understand there is kind of yet another. We already kind of had two different interpretations of the kind of background gauge field. One was kind of a co-cycle, well, a co-chain, which is closed. The other was interpretation in terms of this Poincare dual kind of Poincare dual chain, or kind of, and the gauge invariant data was homology class, and this is yet another, and it has kind of physical interpretation of this kind of network of charge operators. Here we get yet another interpretation of the gauge field on, so G gets E field on M, where G is a discrete group, as a kind of as a map, as a continuous map from M to this Algebraic space. So it's roughly looks in this operation, this gauge field looks like field of a sigma model, right? And where this KGP is a target space of this sigma model. And the but now when I consider kind of gauge transformations, we can understand some sort of homotopies of this map. So the gauge invariant data is a homotopy class. And let me make the following remark. So for you may have seen in the literature this notion of classifying space. And so what is the relation between Algebraic spaces and kind of classifying spaces? So for G with the discrete topology, the first Algebraic planes is the same as what is called BG. It's a classifying space of principal G bundles. It's a classifying space in the sense that there is a kind of canonical principal G bundle over this classifying space BG, and any bundle over any topological space can be understood as a pullback of this universal principal G bundle. And the isomorphism classes of principal G bundle are in one-to-one correspondence with homotopy classes of maps to the classifying space. And the more, but in general, but kind of, and more generally, this KGP is a kind of this kind of piece classifying, kind of applying this B. So B is actually going to use some sort of this classifying functor, which acts on kind of topological groups. So in this case, when we can send this KGP as a this applying this classifying functor of P times. But again, this is just a remark. So what we need for operators, we only need to consider these classifying spaces, and we need this statement that the homology classes are in the one-to-one correspondence with homotopy classes of maps to these Algebraic spaces. And the fact that the Algebraic spaces has these concentrated homotopy groups. Okay, and but for general, this is not true. But for so in general, it's not true that KG1 is equal to BG. For example, if you consider G as U1 with the usual continuous, with the usual topology, it's not true that KU1 is equal to BU1. Okay. Maybe I should, yeah, let me give some examples of classifying spaces. For example, when we consider G is Z, well, it's a very simple case when K Z1 is the same as S1, and this is, you know, so we know that the fundamental group of S1 is Z, and all other homotopy groups are trivial. And we also consider K Z2, and this is confused as CP infinity, and complex projective space, CPN, for very large N. Well, in principle, we can consider a limit n goes to infinity, but again, if we are kind of interested, we consider kind of homotopy classes from some manifold of a fixed dimension. It's enough to consider kind of CPN for large enough n. And maybe another example is G equals Z2. And here, for example, KZ2 1 is RP infinity. So it has S infinity modular action which identifies antipodal points. So, for example, in particular, if we consider Z2 gauge field on some manifold, we can consider it as a kind of this gauge field as a map to RPN for large enough n. We consider it up to homotopy. Okay, why this perspective can be useful? So in particular, can be useful in this in the context of cohomology operations. So so we wanted this by definition, this cohomology operation is a natural transformation of this form. Again, dot means that we can insert any topological space. And but we know that these functors can be understood as kind of applying, okay, instead of considering cohomology groups, we can consider these homotopy classes of maps to Algebraic spaces. So this should be a natural transformation. This is just the same of this form. And so in particular, this means that for like fixed M, if you take a map from M to KG P, so these maps up to homotopy are transformed into maps to kg prime q, again up to homotopy. And from this, okay, there is a this general, so kind of we can use, well, I'm not going to go into detail, but there is this general statement in the category theory about natural transformations and functors, which can be represented as some sort of Holmes in a certain category, and this is called Yoneda lemma. But this basically Yoneda lemma tells us that these homology operations can be understood as homotopy classes of maps from KGP to KG prime Q. And this, well, using this relation between Ehrenberg-McLean spaces and cohomology groups, this can itself can be stood as a fuse cohomology of KGP with coefficients in G prime. So how this correspondence works? Well, one way it's very easy to understand. So suppose we want some cohomology operation which corresponds to a homotopy class of F. So F is a map from KGP to KG prime. And so then we can consider kind of an arbitrary map from M to KGP, and this this map, as we learned earlier, can be understood as a kind of realizes a class in the piece cohomology of M with coefficients in G. And then we consider this map F between Algebraic spaces. And then we can consider its composition. Should be a map from M. But then this composition itself, I can understand as a class in the Q's cohomology of M with coefficients in G prime. And this is what is this we can use to define our natural transformation. It's the value of our natural transformation on alpha. To remind you, so this lambda M should work as a map from H P M G to H Q M. Okay, and so coming back to our discrete to this discrete gauge series. Topological. And topological means we don't want this action to depend on metric or manifold. We only want to depend on its topology. In D dimension. So we learned that these kind of well, Lagrangians are natural transformations HP H, and the kind of the usual case is p equals 1, but the generation to the higher form gauge series is arbitrary p. So usual. And so we had in particular S, so on space-time M, the action was lambda M applied to this B, our gauge field, and evaluated on M. And we kind of wrote it by definition, kind of by this kind of symbolic notation is a kind of integration of Lm of B over M. And B again was the gauge field. E, okay, so how can one now? What is the kind of how can we understand this action in terms of this field? So wilt, which is kind of a map from space-time to Algebraic space. So currently, we can understand B as a kind of class of F, where F is this map from the space-time to this kind of target space, which is Algebraic space. And here we can see that the class is a homotopy class. So what we do is the following. So, well, we can use this. So we understand the kind of previously we understood as this. Sorry, lambda. Of course, I mean here L. So you can see the particular cohomology operation which corresponds to the Lagrange. Of course, it's L. And but using this unit lemma, we understood we can understand this L instead as this element of the disk homology of KGP with coefficients R. And then, so it's a cohomology class in this Algebraic point space, which has the meaning of this kind of target space in this kind of topological sigma model interpretation. And then we just say that S is, in this alternative description, this S is given by integral over pullback with respect to F of this L. This defines as element of HD of M. So coefficients are multiplied. And then we can integrate it away. And okay, and for again for p equals 1 and discrete G, this KG 1 is the same as BG. And well, this group which classifies our Lagrangians is this cohomology group of BG with coefficients are 2pz, which is this group is a marker to E1. And this is the same as this algebraically defined group cohomology. And so this is often you can. So this type of description is this is the kind of description in the original dash graph Wheaton paper. About topological gauge series and group cohomology. In particular, one can kind of define the value of the action actually using some sort of, for example, triangulation of this manifold and putting, assigning to each kind of to the edges like one simplex of triangulation elements of the group, and then to each kind of d-simplex we can assign a value using this group cohomology class, group cocycle. So this is a kind of alternative way which we're not gonna consider. So so here we will use this kind of interpretation of kind of cohomology interpretation, but I wanted to point out that this is the same as kind of considering these elements of the group cohomology, and this cohomology operation is actually equivalent. But and of course, when p is greater than 1, there is no simple algebraic, no more simple algebraic description of these cohomology groups. Like for cohomology groups of higher Algebraic Topology spaces, it doesn't have a like simple group interpretation. I mean, of course, it does have some impressive. It can have, but it's super complicated because it comes from the fact that these Algebraic Topology spaces themselves may be considered as groups, but it's a very complicated group. Okay, so and so the next step would be like how to explicitly we can describe these cohomology operations more explicitly, and actually like so that one calculates this action explicitly on like on a given manifold. This will be next step, but I guess this will be in the tomorrow's lecture. So let me just so next step explicitly describe operations, at least in some cases.